Now, as we start constructing galvanic cells, it's useful to think about if we take two half reactions and put them together in a galvanic cell, which way are the electrons going to want to flow, right? What thing is going to be oxidized, what thing is going to be reduced. And in theory, we could figure this out because any half reaction we write has a known delta G value that we could look up in a thermodynamic table. And there's a relationship between delta G and potential that we talked about earlier in this chapter. And so we could list all the voltages and the associated reactions. So that means they have a value of E. E here being, again, voltage. But one key thing to remember with potentials and potential energy is it's always a difference. So these voltages have to be referenced to something. So because we need to know you can't measure a voltage in a vacuum, right? It has to be a voltage compared to something else. Voltages have to be referenced to something. And so that's where this idea of what's known as standard potentials comes from. We being chemists many years ago, defined a standard electrode for referencing all of the half reactions to. And so the reference that we use is what's known as the standard hydrogen electrode. I don't know why this particular electrode was chosen. It's in fact a fairly annoying electrode to actually make in practice. But this is the half reaction. So this reaction is the reduction of H plus with an activity that is equal to 1. So approximately 1 molar, but not actually 1 molar. The activity is equal to 1. We could say it's a pH 0 solution. Reacting with an electron in equilibrium with, right, and so the product of the reaction is hydrogen gas. But for the standard electrode, this gas is at an activity of 1 as well. In practice, what this means is that the pressure is equal to 1 bar for this gas. If we want to write this as in line notation, we need some sort of electrode, right? Neither of these are solids or metals. So we use platinum as an inert metal, but it's just there to conduct the electrons. It doesn't participate in the reaction at all. So platinum as the electrode. Then we have hydrogen gas, where the activity, let me write that A fancy, activity equals 1. And then with the hydrogen ion solution, an acidic solution, it's aqueous, where the activity is equal to 1. So this is our standard electrode, and we define this electrode to have a potential of 0 volts. So this is by definition, and we reference everything else to this. Okay, and so if we want to measure a standard reduction potential for some other half reaction, we measure it under standard conditions. So standard conditions meaning that we have everything, all activities equal to 1 in our reaction that we're considering. So approximately 1 molar solutions, though not exactly, as we've talked about with activities. And we compare it to the standard hydrogen electrode. So what would this look like? I'm going to switch over to some PowerPoint slides that I have. So in practice, what this would look like, so these are some slides that I've prepared for previous years. We have, so this is what the standard hydrogen electrode looks like. So this is what's on the left. This is defined as 0. So this is 0 volts. So we're just seeing how does the voltage for other reactions compare to this. So if we have, say, this reaction with silver, plus and silver metal, we can construct this galvanic cell and see what we measure. And whatever we measure, we say, okay, that is the voltage compared to the standard hydrogen electrode. So we could then record that the standard potential of the reduction of silver, in this case, or I guess would be positive 0.799 volts. And we could find that listed in a table. And that would be our standard reduction potential. If we go on to the next slide that I have here, this is a little bit of what we can find for standard reduction potentials. One thing I'll note here is that all of these reactions that you'll find in Appendix H in your textbook or online in tables and things like that, these are all written as reductions. So similar to how we write all of our K values for acid dissociation constants, we never write Kb. We just put everything in terms of Ka, and you find Kb from that. Same thing here. We write everything in terms of reductions, even if the reaction would rather proceed in the opposite direction. So for examples, are things with the highest reduction potentials have the most negative delta G values. If you remember, there's that negative sign in the relationship between potential and delta G. So things at the top of this table, like fluorine, really want to give up their electrons and form F minus. So this is, this reaction on top heavily favors F minus. The same thing with like ozone here and permanganate, right? These are strong oxidizing agents. Whereas the things at the bottom of the table, the reaction would rather proceed in reverse. So lithium would rather not be a solid, it would rather react and form lithium plus and give up an electron. So it is a strong reducing agent. It readily gives up electrons. So that's just summarized in this right here. Right, so large positive values mean the reduction is favored and the species is a strong oxidizing agent. Large negative values mean oxidation is favored, the reverse reaction, and the species is a strong reducing agent. Now, and then all of this is referenced relative to what we see here in the middle, our standard hydrogen electrode that just by definition, we define this as having a potential of 0 volts.